thank you very much, Berge. Thank you for your very kind introduction. Yeah, today's talk will be a bit different. And we didn't plan to do this. Yes, it started with work on contextuality, part of which became work on Wigner functions. Yeah, we had never expected to come up with a title like this, but yeah, now it happens. So the title of my talk is something that I will need to talk about. The poster, yeah, thank you very much. The maker of the poster here somewhere? No. But thank you very much for making the poster. I like it very much. And I also want to talk about that a little bit. So yeah, this must be a blob sphere. Well, that could be a pool table. Maybe it is phase space. It could be phase space. But then there's this thing. And I don't know. I will make various guesses during the talk. Yeah, you have an idea? What would you think? Spontaneous.
No, it's just speculating with ChatGPT help. Thank you.
Okay, but okay, well, maybe we can ask ChatGPT still what the idea was. Anyway, I give you my thoughts later. Okay, so let's start with the title. It's a curious title. How many bits for describing it? So this all goes back to an essay by John Wheeler from 1989. And this is the opening paragraph from this paper. It's a rather bulky quote. Maybe I let you browse it for a little bit and then maybe you talk a little bit about the end of that. Let me give you a few seconds. Maybe we can talk more about Wheeler later. That would be nice. Yeah, so anyway, this is something that we came across, and in my understanding, the essay didn't. So he wanted, as I understand it, describe the world in terms of bits. So the entire physics should come out of information theoretic considerations, and he wanted a discrete unit of information. He wanted to base everything on bits. And he described what such a theory might look like, which aspects it should discuss, and so forth. But I don't think he proposed one. And I will propose one today. So I will propose a description of quantum mechanics in terms of a finite number of bits. So we are kicking the state vector or the density matrix into the bin, and we'll be talking about a very finite number of bits instead. So that's what the talk is about. And I think that this might sound a little bit strange, but that is where we will end up. Okay, so much about the title. All right, more on what this talk is about. I mean, it's an unusual talk for me. So this is the area of the talk. We have Foundations Road, we have Complexity Boulevard, and here's our little store. The most concerning thing is our neighbor. So this is David Bohm. So this is something that would have scared me a lot. I remember that. There is an occurrence would have scared me a lot as a graduate student to live next door to Bohm. And so what do we do here? We sell things. We sell hidden variable models that describe quantum mechanics. So on the other side of the road here, we have other people that sell no-go results. So there's the Quotient-Specker theorem, there's Bell's theorem, there's a PBR theorem, and then there's a theorem to Chris theorem. I mean, I guess the better known ones are probably three. And of course, we over here need to be consistent with those, and that's something to be checked. Okay, but a significant role in my talk will be played by Wigner functions and finite dimension. So just to give you an idea of where this talk is situated. Okay, now back to the poster. Yeah, so what is this? Okay, so we could try to look at it from underneath, and then maybe it looks like this, so maybe it is a wave. Yeah, could be. So there is something to be said about wave behavior here. So what I'll treat it as a curtain for now. I will come back to this question, but for now I'll treat it as a curtain. So let's lift it. Let's begin to the left. So what you see here is a Wigner function. A little bit boxy because it lives on a finite dimensional Hilbert space, on a three-dimensional Hilbert space in this case. Yeah, so it is a little bit boxy, but otherwise it's just a Hilbert. It's just a Wigner function. Nothing unusual. It's very easy to go from the infinite dimensional case where the familiar Wigner functions live to that odd dimensional case. And that Wigner function here would have a use in quantum computation, and we'll talk about that. Okay, so then there's something half shown in the middle. Let's talk about that at last. Now let's lift the other half of the curtain. So this is what we will end up. We will end up with a description of quantum mechanics in finite dimensional state spaces. So for us today, for an arbitrary number of qubits, that looks like standard classical probability. So yes, we have the wave phenomena, so we expect amplitudes and we expect superposition, but we will describe it in terms of probabilities and mixtures, nothing else. So it's a classical picture that you come up with. Okay, so this is where this bit from, it from bit thing will live. So this is what I want to get to in this talk. And now the thing in the middle is sort of the turning point. So what we will do is we start out with Wigner functions in odd finite dimension. Then we will turn to even dimension. We will be able to, even the dimension is a little bit more difficult, but we will be able to find a counterpart in even dimension. We'll apply that counterpart to a single qubit, and then we realize, oh, for the single qubit case, we only need probabilities. We need nothing else. No quasi-probability at all, no negativity at all. And then we ask, well, is this a special case, or is it the generic case? And we find it is generic. Okay, so overall the direction is from quasi-probability to probability. Good, here's an outline of my talk. It has 4 parts. So the first 2 are the more conventional parts, and then it gets a little bit crazy. So we start out with a review. I will start out reviewing a particular scheme of quantum computation. It's called quantum computation with magic states. And I will review the use of Wigner functions in that computation scheme. So then I will very, very briefly sketch a qubit counterpart. And then here in the lower part, we are losing negativity. We are talking about probabilities proper. Yeah. So we will devise a hidden variable model for universal quantum computation with magic states on qubits. And then we come to the question, how many bits for it? So that's the outline for today. And yeah, let's get started with that. So part 1, as I said, is a review of quantum computation with magic states and the role of Wigner functions in it. Okay. Can I just have a show of hands about the question of who knows what a magic state is and what quantum computation with magic states is? Oh, that's actually not that many. It's fewer than I thought. I thought it would be half, but it's not like that. So who knows what the Clifford gates are? Okay, very good. Okay, so that's fine. So yeah, so quantum computation with magic state is a variant of the circuit model. It's just that you don't use a universal set of gates. You use only the Clifford gates and the Pauli measurements. That's you have available in your computational scheme, and you know that this is not universal, and there isn't even a quantum speedup if you have these gates only. That's the Goddess-Manil theorem. Yeah, so what's the point? You want to get back to computational universality. And the way you do it in this computational scheme is you supplement those gates with certain states. They are called the magic states. And I mean, in some way, these are very simple states. They are just one qubit states or one qubit states, very simple states, but they are not of stabilizer type. And therein lies their computational value. And invoking these states, you'll get back to universality again by a scheme called magic state injection. I spare you the technical details. Here, just the upshot is you are universal again when you have these states available. So yeah, this may sound as an unnecessary complication, but let me tell you, this is practically a very relevant computation scheme. If you're interested in fault-tolerant quantum computation, this is how you would do it. It would give you the highest threshold, would give you the best overhead scaling. But practical matters are not our concern. Today we are talking about foundational stuff. And so in that regard, the question to ask here is, okay, so the power is shifted from the gates to the states. So what is the property that makes these states computationally powerful? And an answer to this question has been given, well, it's the negativity in their Wigner function. And why this is so, this is what I want to explain to you first. So this is work from the Emerson group, Victor Feitsch. Yeah, it's a little more than 10 years old by now. So let me first read to you the theorem, what they proved, and then let's review the ingredients, and then let's try to kind of in a sketchy fashion, admittedly. Yeah, so let's do that. Let's begin with the statement itself. So here's the theorem. So it applies to odd Hilbert space dimension only. If we are an odd Hilbert space dimension, quantum computation with magic states can have a quantum speedup only if the Wigner function of the initial magic states is negative. Yeah? So no negativity, no speedup. That's the result. Let me just kind of talk about the ingredients a bit. So let's talk about the Wigner function in finite dimensional state spaces. So we have quantum optics people here. So who is familiar with the concept of Wigner functions? Christian does. Okay, it's also more. It was a good show. I was focusing on Christian for some reason. I don't know why. But I think it was a good showing of hands here. So nonetheless, let me just very quickly say a few words about Wigner functions. Yeah, so classical physics. You may think of describing your rock thrown through the air in a phase-space picture. So then in classical physics, you have a definite position and definite momentum, and that position and momentum may change over time. So you have in terms of probabilities, you have a delta peak floating about in phase space. So quantum mechanically, you can't have this because the Heisenberg uncertainty relation forbids it. So then you may wonder, so what's the closest self-consistent thing in quantum mechanics that mimics probability distributions over phase space? And that closest self-consistent thing is the Wigner function. Yeah, but there's one thing about it, and that it's not really a probability distribution. It can take negative values. But other than that, in very many respects, it just behaves like a probability distribution. So the marginals are all well defined and so on and so forth. Okay, yeah, so here you see, you can have negativity, but that's basically the only thing. And in physics, the negativity here is taken as a hallmark of quantumness. And yeah, in quantum computation, you can make this very rigorous, as we should see. Okay, but that's the original Wigner function as Wigner thought of it in position, momentum, phase space. Now we are dealing with finite dimensional Hilbert spaces. So, well, that will take an effect. So here you see the stylized Wigner function of a Qubit. So you have a Wigner function defined on a 3 by 3 phase space. So in general, in odd dimension, the phase space will be dimension times dimension. All right, good. Even dimension we talk about later. But so that's basically the thing that we're dealing with. We have an adaptation of the Wigner function to odd finite dimension. And that Wigner function was described by David Gross. And I will not bother you with the definition. What I will do, however, is describe to you three properties of that Wigner function that will be very important for us. Okay, so here's the first property. We call it preparation independence. And yeah, if your dimension is odd, then you can have a Wigner function which has this property. So if you compute the Wigner function of a state that is a tensor product of two states prepared on different subsystems, then that Wigner function is the same as the product of the two individual Wigner functions. So this is a property that will become important for us, first of them. Second property, covariance. So we need covariance under the Clifford group. And let me explain what this property means. So first, there's a formula for it, and then we will need to take it apart. So what we are comparing here is two Wigner functions. So one Wigner function is of an arbitrary state rho, and the other Wigner function is the same state rho, but conjugated under a Clifford unitary. And now these Wigner functions look very similar. Namely, the Wigner function of the former here, the conjugated state, evaluated at some point in phase space, is the other Wigner function evaluated at some other point in phase space. So phase space points just get commuted. And also this commutation happens in a very similar way. It's just an affine transformation. Yeah, so in pictures. So here we look at a particular Wigner function, just a delta p, and so it's not a quantum state, huh? Not a positive operator corresponding to this, but nonetheless it's a proper Wigner function. And under conjugation by unitary, this peak is just shifted to some other location, and it's easy for us to figure out where it is shifted to. So that's the covariance condition. There's one other property that we need. And that is the preservation of positivity under Pauli measurements. So we have a quantum state rho with a positive Wigner function, and then we measure a Pauli observable. And then by the Dirac postulate, we get a new quantum state that looks like this. So this is a projector corresponding to measurement of that Pauli observable with some outcome. Yeah, so this is a new quantum state. And its Wigner function is also positive. So whatever the initial state was, and whatever the Pauli observable was, and what the outcome was, if the initial Wigner function is positive, so will be the Wigner function after the measurement. So this is also a property of the Wigner function that's rather special, and we are needed. And in fact, we have something slightly more. Also, the Wigner function after is simple. So we can do this again with a delta peak here, delta peak Wigner function. So we take this thing, measure, and we will end up with this bridge. All right, so we are now ready to do the proof of this theorem. So remember what we set out to prove. We wanted to show that if the Wigner function has no negativity in it, so everything is positive, then we have efficient classical simulation of that quantum computation, hence no speed up. With the three properties that I explained to you, it's now very easy to do this proof. So here's the simulation algorithm. So a Wigner function that has no negativity in it is just a probability distribution. So we sample from this probability distribution, and because of the preparation independence of the Wigner function, the sampling from this is actually computationally efficient. So there's no hardness in this initial step of sample. And then we have an update on the Clifford gates and Pauli measurements. Yeah, and they are simple too. So the Clifford gate, the update on the Clifford gates is simple by the covariance condition, and the update on the Pauli measurements is simple by this preservation of positivity condition that I showed. Yeah, so this is essentially the classical simulation algorithm. So if you have positivity of the Wigner function, no speed up. So this concludes the first part, the review part of my talk. So the upshot of this is the following. Yeah, so we need negativity in this particular Wigner function and to have a speed up. Because if there is no negativity, then we have a classical algorithm, that works by probabilistically updating a small amount of data, just a bunch of bits, if you like. It is computationally efficient, but it has this condition. It only applies when the initial Wigner function is non-negative. Yeah, so most states don't have that property. Good. End of the first part. So next part. So qubits, systems of even dimension. So what you see here, these little monsters are Mermin's square and Mermin's star. And they ruin quite a number of things. Yeah, so this is how contextuality comes in to this talk for the first time. Okay, so what's the trouble with qubits? Why are they harder? Right? So here on this axis, we have Hilbert space dimension. We have infinite, that's the domain of quantum optics. We have finite, that's the domain of quantum computation. And it turns out, the Wigner function was originally devised here, but you can adapt it to finite dimension. It turns out that the adaptation from infinite to finite odd is smooth. You almost don't notice that you're switching, but going from finite odd to finite even is very, very complicated, and all hell breaks loose down here. And the reason is that Clifford covariance breaks and positive representation of probability measurement breaks too. And the preparation independence breaks too. So basically everything that we use breaks down. There's a fix of it. And I don't want to tell you about the details of the fix, but you can resurrect the theorem that you have. So we can define quasi-probability distributions with sufficiently nice properties that allow us to keep the old theorem, namely, only if you have negativity, you can have a speed up. However, there is a price to pay. And the price is that the new quasi-probability distribution now lives on a phase space that is larger and has also a more complicated structure. And so what the larger phase space means is that the quasi-probability distribution we use to describe the states is not unique for any given quantum state. That's a non-unique thing. And some people don't mind, but some people don't like that at all. So, I wonder what Berger will have to say about that question later. I'd be curious to know. Yeah, but if you accept it, then there's a way to uphold this theorem. Yeah, okay, so just to illustrate this a little bit, so in the Qubit case, your phase space is just a grid. You can traverse this grid by conjugation of the Pauli operators. Everything's very simple, but now, all right, so this is an important point here for the talk. So these new quasi-probability distributions, they are not unique. So you have many of these guys representing the same quantum state. And some people find that acceptable, other people do not find it acceptable. But anyway, if you are willing to consider such quasi-probability distributions, then you can uphold the theorem that we had before. Otherwise not. Okay, so yeah, so let me be brief here. In odd Hilbert space dimension, phase space was super simple, just one connected component, and you could traverse it by translations. Now, no longer, you have separate components, and they cannot, you can traverse each component by translation, but you cannot hop from one to the other. You cannot even hop from one to every other by a Clifford transformation. Yeah, okay, that's what I want to say about it. So now, what do we do here? So can we admit these non-unique quasi-probability functions? Are they legit or are they not? And so the pro and the con. So the pro is, well, this quasi-probability function is just a tool, and we use what we find useful. Be a pro, and the con is orthodox. So there is criteria out there that define what a proper Wigner function has to look like, and it's a Stratonovich-Weil criteria, and they do not consider it. So for them, a Wigner function is a one-to-one mapping to the states. Okay, leave it open. I don't know, but anyway, yeah. So this is a choice to make. You may do not want to consider such things. You want to have a one-to-one mapping, and if you require that, you go into the area of no-go theorems. You cannot have Clifford covariance. You cannot have a preservation of positivity on the Pauli measurements. Yeah, just a mess. Yeah, but if you permit non-uniqueness, then you can have all these things. So we go down this route. Okay, so now I come to the thing that stood in the middle of my curtain slide. Yeah, so I haven't really laid out the formalism that we use for qubits because there's simply not enough time. Let me just tell you, we can take this formalism and apply it to a single qubit. Then we get something like this. Now we get the 8-state models by Bartlett, Wallman, Bartlett and Wallman. Maybe you'll see it. So certainly you recognize the blob sphere here in the middle. The blob sphere is prime into a cube. So the axes here, x, y, z, are the expectation values of the Pauli operator sigma x, sigma y, sigma z. Yeah. And so a conventional Wigner function for a qubit would have 4 points in phase space that are connected by translation. So for example, the vertices of the gray tetrahedron. And if you use such a Wigner function, you see you cannot represent all states, all quantum states positively. Yeah, that's just quite significant regions that stick out. But if you permit yourself more phase space points, namely the corners of this cube, well, then you can represent all points in phase space positively. Yeah, and so you can represent Pauli measurement and Clifford operations. So everything is positively represented. And now the question is this an exception? Is one qubit an exception, or is it the general case? Yeah. And it is the general case, that it turns out, and that might be a little bit surprising. Okay, and that brings me to part 3, and now we are getting really to the meat of the talk. So everything up to this point was preparation and motivation, and now we are getting to the heart of the matter. Yeah. So, okay, so part 3 of the talk is the definition of the hidden variable model that we deal with, and part 4 will then be working out the consequences. All right. So yeah, so this slide you've seen a couple of times. So here negativity is still a feature, not changing that, but take it with a grain of salt. So our counterpoint is that the above theorem here, irrespective of we are looking at the odd dimensional case or the multi-qubit case, the theorem hinges on a particular definition of quasi-probability function. And we can work with other functions, probability, quasi-probability, and then we will find, no, we don't actually need negativity. It's really a matter of which Wigner function, quasi-probability function you use. This is a counterpoint to me. Okay, and I want to explain that. So here is a summary of the result. So we say the following. So we construct a hidden variable model that positively represents all quantum states, all Clifford gates, and all Pauli measurements. So there's no negativity in any of these objects and no negativity in any of the updates. Everything is positively represented. This is the result. Okay. What is this result good for? So there is, we think, I mean, I'm not really a foundations person, I just stumbled into this, but we think that there is, it could be significant in the field of foundations of quantum mechanics. So our neighbors are Bell's theorem, PBL theorem, Mises theorem, and a theorem due to Ferri. And certainly we have to check. I mean, these are established theorems, and we need to check that we are not contradicting them. And I'll pick two of them later and show that there's no contradiction. Okay, so this is one area of interest. The other area of interest is classical simulation of quantum computation. So, I mean, we are not claiming efficiency of the simulation method. Okay, we have the stabilizer fragment of quantum theory is a very tiny corner of our simulation method, and we reproduce it in an efficient manner. But we also know that our efficient corner is larger than just the stabilizer formalism, but we don't know where efficiency ends. Yet we assume that it ends somewhere. And so this is our open question. So it's a new approach to thinking about the quantum speedup. Good. Okay. So now we're getting a little bit technical. So now comes the definition of our state space. And before we go through the definition, let me tell you about the question. So after we've done all this other work, we studied the work from the Emerson group, and then we did our Qubit counterpart. And after a long time, we figured out what the question was to ask. And so the question to ask here is, for any number of qubits, what is the largest state space that is closed under Pauli measurement? So, yeah, so we have some state space, some set of viable states, and we want to, so that's maybe operators in Hilbert space, and we want to subject them to a Pauli measurement, and then we want to map inside that space. What is the shape of this space that has the property that if you take an object inside it and then apply a Pauli measurement to it, you still stay inside?
What do you mean by applying Pauli measurements?
I mean, this I can write on.
Yeah.
So I mean, so I have an object. So that's like a density matrix, but not necessarily positive. So I have the projector onto the on one eigenspace of some Pauli observable, and I'm conjugating the initial object under the Pauli measurement. Then I have to renormalize. So this is what I mean. And so I want, if this is in my state space, then also this is supposed to be in the state space. So that is my, I want to know, so this is the property that defines this polytope or this space, and I want to know what this thing is. So what took us forever is to figure out that this was the question to ask. It took about a week to answer, but it took a very long time to figure out that this was the question to ask. So, okay, so now this is it. This is this object. So it's operators acting on Hilbert space, on our 2 to the n dimensional Hilbert space with a bunch of properties, and I will go through these properties shortly. But in order to go through this, I need to define another thing, and that's the stabilizer states. So Sn is for me here the set of stabilizer states on n qubits. So we will need that. Okay, so with this, we can now go through these 3 properties here, and they will look familiar to you. So first, the operators in our state space, they are supposed to be Hermitian. And like in quantum mechanics, they are supposed to have trace 1, like quantum state does. And now comes the difference. So, the trace between this operator of interest and the projector onto our stabilizer state, this has to be larger or equal to 0 for all stabilizer states. So this also looks familiar because quantum mechanics is just positivity. It means very closely related to positivity. So if you would require this property for all states sigma, not just the stabilizer states, then it would just be positive. Yeah? So we are requiring less than what you would require in quantum mechanics, and therefore our set of states is larger than proper quantum states. This is, I mean, the proof that we contain all proper density matrices is elementary. We are requiring less. We are requiring less, and so we get more states. Our constraints are linear, so we're getting a polytope, and the polytope has vertices, and basically the vertices is all we are interested in regards to this polytope. Yeah, everything inside the polytope is a probabilistic mixture of the vertices. And the angles of these vertices, this is what is our generalized phase space. You see the definition is very closely related to the definition of density matrices. Just we have a slightly lesser constraint. Good. All right. And then, so please note the change of color in the heading. So this is an important slide for this talk. So this is the main theorem. So yeah, so everything is positive. We represent positively all quantum states. So all quantum states are just probabilistic mixtures of the vertices of the polytope. Then positivity is preserved under Pauli measurement. So as we talked about here, so under Pauli measurement, these operators get sandwiched, and if we sandwich a vertex, then the sandwich can be expanded in terms of probability distribution. So this thing is inside the thing. And these are just these are proper probabilities here. Okay, and also the Born rule we can express in terms of conditional probabilities. So like what you would expect, say for a Wigner function. Okay, and finally we have Clifford covariance. So for every vertex, if you conjugate it under the Clifford unitary, you'll have another vertex. Good. Yeah. So part one we have proven. In the interest of time, I'm skipping the part two of this proof, but if there's interest, I'd be happy to get back to it. It's simple. So at this level of proving the fundamental theorem, things are pretty simple. Yeah, let me just move on here. So then we could also call this a corollary. This is just to observe that, everything is positively represented. Pauli measurements and Clifford unitaries in all states, and precisely the elements we need to describe quantum computation by magic states. So, and that's computationally universal. So we have a probabilistic update representation, like a random walk, if you will, of universal quantum computation, hence of all quantum mechanics finite Hilbert space time. The point is, both states and the operations are positively represented. Good. Consistency checks. So yeah, so maybe this sounds strange. I mean, it's a hidden variable model that describes universal quantum computation. Maybe this is so we need to check, well, there's theorems out there. Are we violating any theorems? And let me go through two here. So there's Ferri's theorem, and the other one I think is PBR that we're going to look at. So yeah, so essentially what Ferri's theorem says that it's impossible to represent all quantum states and all measurements simultaneously in a positive fashion. And we are not contradicting that theorem because we are not representing all measurements. We are only representing Pauli measurements. And that is sufficient for computational universality. And so this is how we sneak out of that theorem. PBR. Yeah, recent result in foundation of quantum mechanics. So it says that any model in which a quantum state represents mere information about an underlying physical state of the system, so that's just a hidden variable model. So any hidden variable model in which systems are prepared independently, have independent physical states, must make predictions which contradict those of quantum theory. So we are dealing with a hidden variable model, and if our model would satisfy this condition of preparation independence, then yeah, it would violate that theory. For our method reproduces all the prediction of quantum theory. So it can only fail to satisfy this property of preparation independence. And you see this right here. If you, let's just say, this is just for matter of explanation, this is a vertex for 1 qubit state, this is a vertex for a 2 qubit state, it is, oh, excuse me, another 1 qubit state, then you might think, oh, the tensor product is a vertex for a 2 qubit state, but no, it's not. It's outside the lambda polytope. And so, yeah, it is not satisfying preparation independence, and thereby doesn't contradict the PBR theorem. Good. Yeah. Okay. Yeah, where does efficiency relation end? We don't know. It's just important for us to point out that we do not claim efficiency relation of all of quantum mechanics. All right. So I'm bracing, and this brings me to part 4 of my talk. And hopefully I'll make it in time. So from how many bits it is called? Yeah. So important point. So what is the it from bit part at all? So the point is that what would quantum systems would usually be described in with a state vector or density matrix, if you like, and that state or density matrix is then updated under whatever operations you have. And now within our setting of quantum computation with magic states, we describe it in a different way. So our state vector is replaced by a vector of bits, it's the bit string, a finite number of bits that are being updated. And what these bits encode is the position in phase space. You have this generalized phase space in which we hop around. And so the bits, they encode the position in phase space where we are at any given moment. All right. And so I think in itself, this is rather strange. So we have a bit string that without any approximations, there are no approximation of real numbers here at all. So a finite bit string represents a quantum system. Good. So for me, this is actually quite fun and strange. Yeah? So we don't need a quantum state here. We get by with a bit string. And so now the remaining question here is how many bits? And so now finally I'll be able to get back to your question. So how long does the bit string have to be? So the naive answer is that the length of this bit string is the logarithm of the size of phase space, the number of phase space. Don't make any dates right now. I'm answering your question. You're checking your cell phone. Please pay attention now. Yeah, okay. So I promised you bounds. Okay, so but that seems intuitively clear, yeah? Number of bits is logarithm of the number of points in phase space, but that's actually the fallacy, but we'll get back to that later. So if we assume this, then we have a lower bound and an upper bound. So the lower bound is from Karanjai, Warman, and Bartlett. So this comes from consideration of contextuality. So the lower bound is quadratic in the number of qubits or number of magic states. And then there's an upper bound. The upper bound comes from counting stabilizer states, essentially. And it is exponential in the number of qubits. So there's a huge gap between the two. And if it was more like that, well, let's start with here. If it is more like that, then yeah, so the processing must be inefficient because even writing down where you are at a given point in time is inefficient. Yeah, on the other hand, it was more like that, and the presumed hardness of the simulation would need to come from something else. Okay, so now we wonder where it is, whether it's more like this or more like that. So we have done a little bit of numerics too. So what is the number of points in phase space? For 1 qubit, it is 8. You have seen it. For 2 qubits, it's 22,000 and something. For 3 qubits, I am told, it's done by other people, it's 10 to the 12. So these numbers, you have 3 qubits, not 10 to the 12. So there's many vertices there. Okay, but that doesn't really matter. Okay, so now here comes the essential idea that allows us to determine the length of the bit string. So if we have quantum computation with magic states, we are always starting in the same magic state. Yeah, it's not varying, it's always the same. So this initial magic state will have some probability distribution over our phase space, and that's the region. Here's the support region. This is what we are starting. That turns out to be small. And well, then when we're starting always from here and continue to measure, we can only get so far. Yeah? Oh, excuse me, that was the starting region. Now, this is what we can reach with our measurements. So we only ever get so far. We will not get into the entire phase space. And the point is, we can figure out what the size of this region is, and it is small. So this is the answer for n qubits or n magic states. Our state vector is 2n squared bits long. Yeah, so it's very short. And that's, yeah, so 2n squared is the answer to the question of this talk. So, so this is the proof of this result in the simplest possible fashion, but I'm leaving out steps. So you can show that you may restrict yourself without loss to commuting Pauli measurements. I mean, still, subsequent measurements may depend on earlier outcomes, but you may restrict yourself to commuting Pauli measurements. Also, you don't need to invoke this restriction if you don't like it. But that leads to the simpler proof, so we might use it here. Okay, so let's work under this assumption. So then there is a theorem due to Theodori that says that limits the support of the probability distribution, say for the initial state. So I mean, we have super many vertices, but the size of the support, I mean, how many elements we have in our probability distribution, this will be the dimension of the polytope. And the dimension of the polytope is 4 to the n minus 1, so roughly 4 to the n. And so, yeah, so we have 4 to the n elements in the probability distribution, so each element is labeled by 2 n bits. So this is, so every sample for the initial magic state is described by 2 n bits. And then come the measurements. Since they are all commuting, we can have at most n of these measurements. In each and every measurement, well, you need to specify the Pauli observable on n qubits, makes 2 n bits. You need to specify an outcome, makes 1 bit, and then you have a post-measurement distribution, again by Theodori. Each sample drawn from it is described by 2 n bits. And then, so every vertex you can reach in this process together is specified by all this number of bits, and you just count them, and it gives you something like 4n squared. Yeah, okay, I promised you a 2, I only gave you a 4, but that was all a little bit sloppy. You can do it better than what I did. But what you see here is the quadratic scale. Okay. Yeah, so the upshot is we have again a classical simulation algorithm. The amount of data is small, is this time it's quadratic in number of magic state. The efficiency or inefficiency is unknown, but it is always applicable. There's no condition, yeah, because there's no negativity. Good. This is basically the end of my talk, and my time is also up. Okay, good. I just want to advertise these lambda polytopes as something fun to consider. I think it gives you weird phenomenology that you would a priori not expect. this is the works that I presented today. Final comment. So let's get back to this poster. So I've been using what this might be, and maybe it is a wave. Maybe it is a wave put into a box. And if that is so, then this is our version of it. Thank you very much.